Good afternoon, everyone. My name is Jae-Bom Jung, developer working at Ultron Research. So, title of today's talk is the Beyond the Basics of Graph and Network. So, I'm gonna start from some history of graph functionality in Mathematica, and then show some applications. So, without further ado, let's begin our exploration of evolution of graph functionality in Mathematica. Before we delve into detail, let's go back in time to version 8 of Mathematica. I mean, like prior to version 8. In those early days, graph functionality existed, but as separate packages, which had some limitation. For example, like some performance issue with large graph, and it's not easy to integrate with other functionality in Mathematica. So version 8, we make a significant transformation. So like graph and network functionality now fully integrated into Mathematica as the system function. So it's not package anymore, or like high performance scalable data structure with over 140 symbols. So for example, like a graph now stored as some data structure, it basically it has three different structure. First one like a linked list, and then the other one is matrix, or the simple sparse matrix, or the sparse array matrix. And version 9, we added another 50 new functions, including the support for network flow that enable to solving the maximum flow and minimum cost of flow problem, or other related the problem like a cut, vertex cut, edge cut, all those things. So we also introduced some performance improvement, enhanced graph distribution. So now we can easily handle the like a statistic or probability related to graph functions. And then also the Hamiltonian cycles and Eulerian cycle support, which is now much faster than before. And version 10, we do further progress and capability. We now have support for multi and mixed graph. So multi-graph basically the graph with the multiple same edges. For example, like if we have edge from A to B, then we can have more than one such edges. A mixed graph is a graph with directed edge and undirected edge. And also we adding some automatic 3D visualization and and the ability to address complex problem like the traveling stage problem with the function called like a find Postman cycle. And version 11 now, we introduced more graph constructors. So for example, like nested application of functions, nest graph, and new graph properties for curated data, and domain-specific network like chemical data and Wolfram language data. And also there are another performance improvement. And version 12, we kind of marked significant step toward improved aesthetic and usability. So we refreshed and unified the overall aesthetic for graph visualization, introducing a common default appearance and each set of plotting. So in addition to the plotting we had before, which is kind of graph specific, we adding more plotting. Also, we add some generalized plotting that used the over the other plot functions. for example, like a detail and simple such things. And we also improved functions and comprehensive support for graph properties. So the user experience more productive and user friendly. So for example, like we have the properties or options of graph, for example, like styles or coordinate everything. And then we have some another function, create the new function out of those original function, for example, like subgraph. So if original graph have options, it wasn't that clear how we handle those options to, for example, like subgraph. But with this improvement, we can now easily inherit all the option of the original graph, or we can just select the property we want, or just take nothing for performance. And now comes version 13. So in version 13, we take another leap forward, like we expanded our capability in computational geometry and introduced powerful function for computational topology. And also we provide a versatility annotation framework, including edge tagging for multigraphs. So edge tagging allow precise differentiation between multiple edges connecting the same vertices. What it means is when you have multi edges, it wasn't clear to how to specify the style, for example, style of those two edges, because it has the same. So if you want to separate those two edges by color, red or blue, previously it wasn't possible. We can hack it, but it wasn't clear enough. So adding tag means when you specify vertex, I mean edge, or edge, undirected edge A, comma B, comma B, and then we have a third argument that can be used as tag, for example, A and B. So because of that, it is very easy to now the styling those edges with different color, even it's the same edge. Also, yeah, in version 13, the development include new functions for computational topology, which is critical of representing complex structure. So for example, like we have mesh connectivity graph that can get the topology structure out of mesh object and construct a graph that represent it. And then we also have like a planar graph related function, dual planar graph, also like a planar base list, which is more like geometry function. So far until now, we have over like 260 graph symbols now available in Mathematica. And you might wonder what could we do with all this power. So as you can see, the evolution of graph functionality in Mathematica has been remarkable, offering broad range of tools and features for various applications. So now let's transition to some case study to see this capability in action. So our first case study focuses on the importance of strengthening the US food supply chain, as highlighted by Niter Corporation's analysis. So this paper is called US Food Supply Chain Security. And if you can click this link, you can see you can landing to their page like you see in the slide, and you can get the more information from the papers. So the Niter Corporation conducted a network analysis, and their finding provide valuable insight into these critical issues. So what it does is like they focused on the US food supply chain. They examine key hubs and transportation route to assess its resilience. The study revealed key findings, notably that the US food supply chain is vulnerable, particularly in certain key hubs. So, in response to their finding, MITRE made a recommendation to enhance the resilience of the food supply chain. These recommendations include data sharing, a system-oriented approach, and operation risk assessment. So like the tool they're using, mostly the Mathematica, functioning Mathematica. And then for example, like here you can see, they form the graph that consists of those all the hubs and the route. And they're using graph to visualize the relationship, like you see here. Also, they're using the graph to identify some critical hub using some centrality and some degree centrality, for example. And the next project is the Wolfram physics project. So this is about to explore the project, explore the fundamental physics. So this project explore the quest for fundamental theory of the universe by investigating minimalist network models. So here again, you can click this link to go to the Wolfram physics page, and it has all the value information you can see here, like project announcement, latest bulletin, and it's still ongoing project, and it has lots of information. So to simply say, this the model, the minimalist network model, offer fresh insight into the connection between mathematics and fundamental physics. And this project introduced structureless model that demonstrate remarkable complexity and potential like relevance to understanding known features of fundamental physics. And in those combined empirical investigation with mathematical analysis, offering fresh perspective on the universe. So like the tools used for this the project, again, there are like the documentation. You can go by clicking here. So it's a Wolfram Physics project function. So this is a list of functions that used for this project. So many functions, the last function here built by the graph functionality in Mathematica. Also, these functions create the interesting graph, like the model, the physics that created by this project. And actually, this function is in Wolfram function repository, the website. This is another website that created by the Wolfram. So actually, this website is good. The good thing is you can, if you have some function you create and use a lot, and thinking that function also useful for other users, you can easily publish the function in Wolfram function repository. And only thing you need to do to use the function is just type resource function and name of the function if that function is published. So here's some example of resource function, the Wolfram, the physics project function in Wolfram physics project. So for example, like Wolfram model plot, this giving you plot of this collection of relation. And also there are function like a hypergraph to graph. So once you have this Wolfram model that giving you final state, which kind of hypergraph, and then you can convert that hypergraph to graph. And using graph 3D, it plotted as 3D graph. Also, you can plot multi-way system. Create multi-way system state graph, which is certain stage you specified. Okay, so lastly, our third case study explored the analysis of COVID-19 data. So this work done by Dr. Hiroki Sayama. Actually, you can go to this community, wolfram.com. This is another user community that run by Wolfram. So if you go there, user freely, create post of your work, user's work, or whatever you have. If you have any question, you can also ask there. It's very useful site. And this example you see here is the leverages the vast amount of data generated during the pandemic to uncover the interconnected nature of our globally connected world. So the result of this analysis are including a correlation network that was created using the daily change exponent, revealing 3 major global communities. So like a community 1 that represented by Europe, North America, and Southeast Asia displayed distinct patterns during the pandemic. And another community 2, for example, including the near Middle East, Central South Asia, and Central South America, responded differently, influenced by variant impact. And the community 3, the large community, consisting of Africa, Central East Canada, and Australia, saw limited activity until the Omicron variant led to a significant spike. So this community structure were consistently identified under various settings, providing valuable insight into global pandemic progression. So, like here is one of little bit of code snippet from the analysis. So this is one of the example how he identified the community. So actually the node here is the region or the country. And then this is how they build the edges. For example, they measure the correlation between the regions. If it's greater than certain threshold, they put the edges. And the edge way will be those correlations. So they build the edge and edge way and the node name by the country or region. So they built a graph with these informations. And then they find the communities using the function called find graph communities, method modularity. After they finding community, then using community graph plot to show, to display those communities. So graph G, and then the communities and the neighbors and other options to visualize this community. So as you can see, these two are kind of small community, and then here you see the 3 big community that also mentioned. So, and this is all I have for today. So thank you for listening my talk. And here's other talk you might be interested in. One is already given yesterday called Graphs in the Modern World. This is actually another case study that how to use the graph for doing some study in real life. So if you haven't attended that talk, you can check the agenda, and then you will probably get a notebook or even the recording. And also there are office hours tomorrow at 8:30 in the morning. So if you have any graph related questions, you can come and join these office hours and ask anything you want or discuss. So again, thank you for joining today, and I hope you enjoy this talk. Thank you.
All right, J-Bum, if anybody else has other questions, I saw you were answering a lot of them in the Q&A chat. If there's any more you maybe want to explain in greater detail or anything.
So I just got a question about let me see, what code. So I uploaded the presentation notebook on the handout, and actual code for like a last example, you can click the link community, then you can see the code in there, if that's what you're talking about. Oh yeah, so another question about multiplex and multilinear network. Yeah, we don't yet currently have specific like algorithm and function to handle those network. Only thing I can say is like I answered is like a layered graph plot, or you function layered graph or layered graph 3D, which currently is only for kind of visualization. So for especially 3D, layered graph plus 3D is showing the layer by layer. But yeah, we will see how can you integrate those things with actual multiplex network in the future, but we don't have it right now. Just the visualization for sure. And another question I answered is about Hamiltonian graph Q. Use exact method for suitably small graph and heuristic when the graph get too large, and can graph be directed or undirected? So yes, actually not small or large. We have several steps to check the Hamiltonian. So also we have several methods inside. So it's kind of going through the easy negative area, for example. So there are some theoretical background that you can easily check it's not Hamiltonian graph. So we go through those steps, and then we, depends on the graph type, we go to heuristic, or at the end, the last method will be the exact method, which also is not just exact method. We have the specific, some kind of algorithm that checking the Hamiltonian cycle very quickly. And Hamiltonian graph Q, you can check both directed or undirected graph. So it seems like there is no question anymore. So again, thank you for joining this talk. And if you have any question in the future, today, if you come up any question about graph or even geometry, there are, the office hours tomorrow morning, like I said, in 8:30. So feel free to join that office hours with any questions or concern. So thank you again, and I hope you enjoy the rest of the conference.